So in a previous problem that we solved, we had a incompressible viscous flow of air that was flowing between two infinitely long parallel plates, and they were both separated by a distance of d. Now in that example, we had no pressure gradient existing in the flow, and we had essentially a velocity of 0 along the bottom plate and a velocity of u sub e along the top plate that was non-zero. But now for this problem, what we want to do is we want to build off of that, and instead we want to say that both the top and the bottom plates have a 0 velocity for the flow, and there will be a pressure gradient that exists in the flow. So off to the right here, we can actually see what this will look like. It'll be kind of a parabolic shape, and we'll also see this by working out part A for finding the expression for the variation of velocity between the plates. So let's get started working on that. So for part A, we can actually say, since the layers are infinite, we can say that u is going to be a function of y only. The velocity in the y direction is going to be equal to 0. And since we have a pressure gradient, we can say that pressure is actually going to be a function of x. So last time what we did was we started out by defining the x momentum equation and breaking it down for the problem. So let's do something similar to that, where we have the boundary layer x momentum equation, and we're only focusing on the x momentum equation because we only have flow going in the x direction. Now this equation started out with the substantial derivative. So we had rho, or the density, times capital du over dt. And that was equal to rho times u times del u del x plus rho times v del u del y. And that was equal to the negative pressure at the edge divided by dx, and then we'll have del over del y times mu, again, times del u over del y. So then in this problem, essentially what we have is, since v is equal to 0, this term will go to 0, and then since u is only a function of y, this term will also go to 0. So essentially this will be equivalent to 0 overall. And then here it's saying that dp dx is equal to some constant. So then we'll essentially keep this term on the right side, and we'll set that equal to 0. So let's write this out here. So we have 0 is equal to dp dx plus del over del y times mu del u divided by del y. And the reason I took off this negative here for the dp is because we actually have a mix of both positive and negative changing flow. So we're not entirely sure at what point we're at in this flow to confidently say whether it's positive or whether it's negative. So that's why I just left it as positive for now. And then we'll work with it and then see what it ends up being. But anyways, from here what we can do is we can start to integrate with respect to y. To start breaking this down so that we get some sort of function with respect to u and dp dx to work with. So let's integrate with respect to y after we subtract dp dx to the other side, such that we'll get negative dp dx times y plus c1 is equal to mu, and then we'll have del u over del y. And then we'll integrate again, such that we get negative dp over dx times y squared divided by 2 plus c1 times y. And then we'll also have plus c2, so we'll have another constant of integration. And then that'll be equal to mu times u. So now the next step that we can do is we can look at the boundary conditions. So at y is equal to 0, the velocity is also equal to 0. So with this in mind, we can plug in those values. So we get dp over dx times 0 squared over 2 plus c1 times 0 plus c2, and this will be equal to mu times 0. So here we can infer that c2 is going to be equal to 0. And then now for the second boundary condition, we have at y is equal to h, u is going to be equal to 0 again. So we'll have negative dp over dx, and then we'll have h squared divided by 2 plus C1 times H, and then C2 is equal to 0. And then that'll be equal to mu times 0. So then we get that C1 is equal to dP dx times H divided by 2. So now with all of this information, we can then solve for U. So we get that U is equal to 1 divided by 2 mu, and then this will be multiplied by dP dx, and then it'll be multiplied by H times Y minus Y squared. So we can actually see from this equation that we're going to have a parabola, and that is exactly what we have drawn up here. So it matches out. And then that is part A. So now for part B, what we can start out by doing is writing the equation for shear stress, because that is what we want to try to obtain. We want to attain the expression for shear stress on the plates in terms of dP dx. So what we can start out by writing is shear stress, denoted by tau, is going to be equal to the viscosity mu times du dy. So we can say that du dy is going to be equal to 1 divided by 2 times mu, and then we'll multiply by dP dx because all that is constant, and then we'll be left with h minus 2y. So then we can actually say that tau is going to be equal to dP dx times h divided by 2 minus y. And we are almost there. So now what we can do is we can figure out what tau is both on the top layer as well as the bottom layer or bottom plate. So we can say, oh, there we go. We can say at y is equal to 0. So we'll have tau is equal to dP over dx times h divided by 2, because essentially y will just drop out. And then for the second one, so essentially the top plate, y is equal to h, then tau will equal dP dx, and then h divided by 2. So now you might be thinking, wait a second, how do we have positive for both? Because at the top layer, we'd have h divided by 2 minus h, so we should have negative dP dx times negative dP dx times h divided by 2. But the reason we actually have positive is because at the top here, notice we have a negative, essentially du dy. So we'll have to take that into account when we're calculating for the shear stress, because when we're at the bottom here, it's going to be positive because we're having a positive increase for du dy. But then here we'll actually have that second negative, which will double up with the negative h over 2, to then make it positive because we have a negative slope. So that's another kind of sneaky thing that we have to keep an eye out for when calculating for this. So what we can say is that tau is going to vary linearly, versus in the other example, tau was actually constant because we didn't have a pressure gradient.